Welcome to our meeting, everybody. I'm the president. I am currently running this show from home, but I will be back down there to see you shortly now that I've got the thing going. But I'm going to start by introducing our speakers tonight. We have Jennie Starstuff King, who definitely looks like Starstuff tonight. And she is a NASA Solar System ambassador with a degree in astronomy. While studying astronomy and physics, she discovered her love of science education through working with elementary school students. As a high school physics and engineering teacher in Colorado, she taught her love of space exploration to the classroom. Jennie now manages education programming for Science World, and her female co-pilot is called Kepler. James Tauber is a doctoral candidate and programmer with a background in linguistics, mathematics, and online education. He was involved with the development of web standards like XML, and worked as a software developer in the industry for over 2 decades before returning to academia, where he now writes open source software for studying texts and crafts online educational experience in both the science and humanities. He's also, well, actually, it turns out they're both major Tolkien fans, but he is actually a Tolkien scholar. So I'm going to hand that over to you now, Jennie and James. Take it away.
All right, fantastic. Thanks so much. I'll try loud enough that I'm heard online and in the room, and I'm getting nods from the back of tells me my volume is workable. Yes, again, hello. My name is Jennie King. Sometimes I do go by Jennie Starstuff.
And I'm James Tauber, and I sometimes go by James Tauber. So in 1801, the 1st of January, the Italian astronomer and priest Giuseppe Piazzi discovered what could possibly be the planet that had been predicted to exist between Mars and Jupiter. The problem was, after he observed it, he couldn't find it again. And this became a big issue amongst astronomers in 1801. And no less a mathematician than Carl Friedrich Gauss developed new methods to identify the locations of celestial bodies. And Gauss's methods worked particularly well because by the end of that year, in December 1801, and then again in January 1802, people were able to observe Piazzi's celestial body, what we would now classify as a dwarf planet that Piazzi named
Ceres. And some of you may be familiar with Ceres. It was, of course, the first asteroid to be discovered before we had such a term as dwarf planets. And Ceres, of course, now we know is one of many asteroids in that asteroid belt between Mars and Jupiter. But Ceres actually comprises about 35% of all of the mass of that asteroid belt. So this was a pretty big deal of a discovery. Now, this act of doing these calculations in order to figure out the location of something in the sky, that's something that people had been doing for hundreds, if not thousands of years. And that's something, those kinds of calculations are something that we refer to as an ephemeris, which is probably a term that you may be familiar with. But before we go into behind that term and the calculations of such objects in the sky, I happen to just coincidentally be standing next to a classical philologist, and I feel like I should take advantage of that. Can you tell us a little bit about the history of the word?
Absolutely. So many of you will be familiar with the describing things as ephemeral as well, and might wonder what that has to do with the ephemeris. Well, the ancient Greek word ephemeros, which means daily, is made up of two parts, epi and hemeros. And so in the sense of something being ephemeral, it just means that something only lasts a day. But in the context of the word ephemeris, it came to mean amongst the ancient Greeks a diary or a journal, things that happened on a day. And within the context of astronomy, that meant what were the locations of the celestial bodies on a particular day.
We like to keep it pretty cross-curricular here, not just science, but linguistics and history as well. And speaking of history, I'm going to give you just a few snapshots, really a quick whirlwind tour of some of these examples of ephemeris and ephemerides being calculated over the years. So one very early example that we have is this papyrus fragment, which is from the 3rd century AD, and it is part of the ephemeris calculations that Ptolemy did in the 2nd century AD. So these were happening quite early on, these kinds of calculations. If we fast forward a little bit beyond that, we end up in 9th century AD. We have a scholar named Al-Khwarizmi, and he calculated what was called a siege, which type of this ephemeris chart. What you see on the slide here next to his statue is actually a later Latin translation of this. So he, though, was primarily known not necessarily for this siege, but for actually and who gave us the word algebra, which may or may not make him popular with school children. We're math nerds, so he would be popular with us for those reasons. Now, again, just some snapshots, not a comprehensive picture at all of the history here, but of course, many of you would be familiar with Johannes Kepler. Johannes Kepler being famous for quite a few things, including ephemeris calculations. We, of course, named a telescope after him, and I do have a cat named after him as well. Though I will tell you a little secret, I technically named my cat after his mother, Katharina Kepler. That is perhaps a topic for another discussion, but that over the course of those centuries, right, even thousands of years, the general practice of calculating this type of information was pretty much the same, right? The math became more advanced over time, of course, but it was this sort of painstaking manual calculation of making all of these tables. But then if we fast forward way even beyond our friend Piazzi here, and if we fast forward even into the mid 20th century, a couple of really big changes occur, right? One of the big changes that occurs is we now have electronic computers that can assist us with this sort of thing. And the other big change that occurs is that we are not only interested in knowing two-dimensionally what is the location of something in the sky, we're interested in actually being able to send spacecraft out to rendezvous with or make flybys of various bodies. So we now need to be able to calculate the locations of these bodies in three-dimensional space, because otherwise, how would something like the Mariner 10 mission make flyby Mercury and Venus? And then when we get to the Voyager missions, how would Voyager then be able to make these amazing flybys of the outer planets that we learned so much from? And this, of course, is laboratory in California enters the chat. So they've basically going on at this point is teams of mathematicians and engineers and scientists that are doing all of these sorts of calculations for all of these individual in order to make sure that they can meet their mission. But having said that, it would be really nice if there were an underlying set, a centralized place for information from for all of these different missions and the milestones that they're trying to meet. And so luckily, if we just fast forward even more and we head into the 1990s, we have an engineer at JPL named, he develops and implements a NASA called Horizons. And Horizons is taking advantage of the fact we now have electronic computers to help us. And that's this centralized platform where all of these NASA engineers, mission managers, and all of these different scientists use in order to plan their missions. And of course, that turns out to be really helpful, right? Because variety of different missions. They're trying to do these very complicated things to a high degree of precision, these flybys, gravity assists, and so on, right?
Yeah, and speaking of flybys and gravity assists, when Jennie and I first met and discovered our common love of astronomy and space probes and missions like this, one of the things that we were frustrated by was it was very difficult to find out when certain...
It's the, 10 seconds of terror, the 6 minutes of terror that they get sending things to Mars.
Yes.
Is at least a little reduced.
Exactly. Okay, so we built this site, Space Missions, available at space-missions.com, and it gives you a timeline of upcoming events, past events, for all of the probes that we've entered the information for. So you can see when Psyche's going to get a Mars gravity assist, for example, or where the various perihelia of the solar orbiter took place, and so on. You can drill down into particular missions as well to get just the events related to that mission. If the slide does change, I did push the button, but it's going. You can drill down to a particular mission like Juno, which ended recently, and oops, I've gone way too far. My lesson, sometimes it's very fast and sometimes it takes 10 seconds to...
There's some variation in there, you know?
Keeping us honest.
It's the light travel time.
Yeah, there you go. This is... It's still, yeah, exactly. drill into a particular mission, and in this case, Juno, and see where its various gravity assists took place, and orbital insertion, and so.
Now, we, had thought to ourselves, wouldn't it be amazing if when we were making this website, if we could have access to all of that fantastic ephemeris information from Horizons that exists at JPL? But, surely you have to be a NASA insider in order to access these things. But spoiler alert, and we've had a couple of times spoiler alert now with the slide reveal, that if you go to this URL on the screen, Horizons is, of course, available to and available to use for amateurs, for people who are not working. We did then take advantage of that in order to integrate that into our website.
Yeah, so there's a web interface to Horizons that anyone can use. You can select what particular body you're wanting to generate an ephemeris for. You can set your observation point to not just the Earth, but any other body as well. So if you're wondering where the Earth would be in the sky on Mars, you can look that up as well. You can pick a particular time or time range that you want to generate the ephemeris for. So it's not just about what's going on now, but what was happening decades ago, even centuries ago in some cases, and also what's going to happen in the future. And then what gets generated from this is the detailed ephemeris, which will come up in a moment, I'm sure.
Yeah.
Shouldn't need that, but we'll give it a go. There we go. So this is the ephemeris that gets generated. So it's got a bunch of information. In this case, we set it to calculate just once a day, but you could set it to do every hour, every 5 minutes if you wanted to. You can see along the columns, and some things will pop up in a moment if the button did work. It's giving us things like that because we're wanting to express this from the point of view of Earth, but it's also giving us some additional information like this delta and delta dot, giving us information about how far the object is away from us and also what velocity it's traveling, so whether it's going away from the observer or towards the observer.
Yes, it has in fact changed number.
So maybe you should stand there and confirm that the button worked. Anyway, so underlying all, there are literally hundreds of thousands, if not millions, of objects that are in Horizon. So we're not just talking about the planets, we're talking about every probe, hundreds of thousands of asteroids and so on. And under the covers, they're all given a particular number. And so Mercury is 199, Venus is 299, Earth is 399, and yes, there'll be a quiz, so pay attention. The spacecraft, you'll notice, get negative numbers. The asteroids get numbers which generally correspond to the number that they're named. And
so if you thought that what he said about you were serious, there is a quiz and it starts right now. And the stakes are very low. The stakes are, you can feel proud of yourself if you know any of the answers to this, and otherwise it's completely fine. This could be interesting with the delay though. We might spoil some answers. So you had a very brief glimpse at the sort of numbering system that exists in the Horizon system. So does anyone want to take a guess at what sort of number we would assign, or what number we'd assign to Mars? Yeah. Let's see. That is correct. 499. Right away. I think I pressed with feeling. Okay. So give it a little more passion on the button
that's
click.
My problem.
Yeah.
Press it like you mean it.
Yeah, exactly. Okay. Like you're launching something. Exactly. Fantastic. So yeah. Then maybe for our next one, we could just shout out, what do you think Jupiter is? 599, exactly. Yeah, you're welcome to shout. It doesn't have to be a whisper. But indeed, Jupiter is 599. So if we move on to another example, ooh, this is a fun one.
Question.
If you know anything about the history of our labeling of Pluto, what do we think Pluto is? Well, but when was Horizons developed? So Horizons, it turns out, was developed in the 90s, right? Which means at the time that Horizons was developed, we were still classifying Pluto as a planet. This was a bit of a tricky one. This was a mean one to choose, but I do think it's fun. As far as Horizons is count as a planet in the numbering system. Okay, this might be another trickier one. So I'm giving you a number instead of a picture of something. What do you think 301 might correspond to based on what we've seen so far? The moon. That wasn't a tricky one at all. Everyone got that immediately. Okay.
That's amazing.
My test of what is difficult question or not may not be super accurate. Okay, how about this one? This asteroid with the lovely name 152830 Dinkinesh. for the number? 152830 is exactly right. Yeah, I thought it'd be funny if we could have gotten a chorus going of people trying to say that synchronized. Would be quite a funny thing to happen. What type of object do you think 6775 is? Good guess. It is indeed an asteroid. It is indeed an asteroid. And in fact, it's not just any asteroid. It's 6775 Giorgini, named after John Giorgini, the creator of the Horizon system. So he does have an asteroid named after him now. That's what a big deal this Horizon system is, that you can have an asteroid named after you. All right. And finally, negative 121 or minus 121. What type of object? Yeah, spacecraft. There's absolutely no way for you to guess which spacecraft. Does anyone want to just try to throw out a spacecraft? This one would be pretty tricky. Yeah, great guess. It could be literally any spacecraft, right? In this case, it is in fact the Bepi-Colombo spacecraft, which is actually a European Space Agency mission to Mercury. So we have all of those, and honestly, sometimes the best thing to do is just to type in the name of the object, because obviously we get tricky with some of the numbering and naming of things on occasion. But one of the things that we found out with using Horizons personally on our website, where obviously our major concern and our motivation for making this website is that we want to be able to collect in one place. Hey, is there a flyby of anything happening this month? Is there a gravity assist happening in the next couple of months, right? One of the things that we discovered, as in the example that I'll show here, is that when we were looking for certain deep space maneuvers or certain flybys or gravity assist and things like that, when we couldn't find that information publicized anywhere, we could actually use Horizons, run this system and generate a table and be able to determine what was happening. So this is an example of looking for when a deep space maneuver of the Hera mission, which is a mission that's going to check out the aftermath on purpose, not accidentally. And we were able to look and generate this information in order to see how the numbers were changing and what that meant in terms of when that event was happening. So you can really do a lot of fast problem solving by having access to data like this.
So what we'll manually use the web interface and key things in again, but what we did was take our software, talk computer, pull down the ephemerides for all of the bodies that we were interested in, and then process it on our site. And we're finally able to do what display on our site the location of the bodies. So in this case, you can go to the page for the JUICE mission, see where JUICE currently is, where the relevant bodies like the Earth, Sun, and Jupiter and its moons are located at any point in time. So here we're showing where it was on the 7th of March when we took this screenshot. In some cases, Jennie mentioned the DART mission, the one that delivered an asteroid. That doesn't have a current location. Back to the last known location, which is exactly at the point where it hit the asteroid. And apparently our internet connection is unstable. You're not the only one. I think it's the pressing with feeling needs to be on. So John tells us that Horizons receives about 50 million queries a month from 40,000 different IP. In its history, it served up 2.2 billion ephemerides, which is pretty impressive stuff.
And so Horizons, though, of course, I mean, we've got pictures of JWST and Hubble being thankful. I know we're sort of speaking on their behalf, but I'm sure they're thankful because Horizons is, of course, used as the back end of these big space telescopes and other space missions that are doing amazing science on behalf of NASA out there, like JWST and like the Hubble telescope. But it turns out, and John told us this as well, that Horizons has been used for a variety of things that are maybe not what you would think of or expect, not necessarily NASA missions. So the Horizon system and the data that it is able to generate actually has been used in order to establish the provenance of a painting in legal proceedings. It has been used by researchers in order to check the alignment of Stonehenge. And even at one point, researchers used Horizons in order to correlate dolphin vocalizations with the angle of the moon in the sky. So yeah, dream big beyond regular space mission related applications. Horizon actually branches out quite a bit, sometimes into noise noises that dolphins make. But of course, it's all well and good to be able to calculate where something is going to be at a given time and be able to do these flybys and maybe take some pictures. But that doesn't really do us as humans a whole lot of good unless we're able to communicate that data back to Earth, right? On the other direction of that, of course, sometimes we need to communicate out to a spacecraft in order to tell it, hey, navigate around an obstacle or change your trajectory, or in many cases, in order to do a software update from the ground out to a spacecraft that we can't really send someone out to in order to fix that. And so in order to solve that problem of being able to handle that communication piece so we can actually get that science data and keep those missions running, luckily we have something called the Deep Space Network. And both of us are really big fans of this Deep Space Network. So the Deep Space Network consists of these clusters of antennas that exist in 3 different locations around the world. So in California, in Spain, and in Australia. What's great about these is they're fairly evenly spaced, about 120 degrees apart. Having the turning of the Earth, which turns out to be a bit of an obstacle, not only for certain aspects of ground-based astronomy experienced, but also for communicating with spacecraft that are overhead, it allows us to stay in communication and continue receiving that data or transmitting that. Now, one really fun way to explore this, which I highly recommend that you try after this, if this is your idea of a fun Friday night, which I guess maybe it is for me, is that NASA actually made a game about the Deep Space Network in which you control the antennas and you try to catch the data coming down as the Earth is turning. And so you're zooming by all of these different locations and you try to beam data back up. And I encourage you to be better than me because poor Juno up here, this is a screenshot of me playing the game and I'm just beaming those ones and zeros straight past Juno and into space. So hopefully that was not an important update for that mission. But it's a great way to demonstrate the fact that we use all of these antennas around the world to collaborate with each other in order to make that happen. Wow, James, what's going on this slide?
Yeah, well, so that's me when I was about 8 years old, standing in front of one of these dishes that forms part of the Deep Space Network. This is the largest dish at Tidbinbilla, just outside of Canberra, where I was born and grew up. Yeah.
So did they let you inside the facility?
Unfortunately not. This fence was as close as I was allowed to get, as much as I would have loved to have been able to go inside. But Jennie, surely you, as a NASA Solar System ambassador, have been given access to all sorts of top secret NASA things.
Well, I mean, I had and tell everyone in this room and online that I did travel last year all the way to the center of the universe in order to obtain and as you can see up on those screens at the front of the Mission Control Center at JPL, they've actually got antennas from the Deep Space Network on there showing where they're pointing and what missions they are communicating with. But here's a fun fact. You don't have to sneak into a NASA facility in order to get that information. All of that information is also available to everyone. They make that available to the public. If you go to this Deep Space Network Now website, it does what it sounds like. It tells you what these dishes are pointing at, what they're communicating with at whatever time is now for you at the time that you go to this website, right? Which turns out to be really interesting. In this case, we see an example of one of the dishes in Spain that was communicating with Voyager, which now has about a 2-day round trip light travel time when we're communicating with it. So it's good to keep in constant communication with things like that. We also then decided, well, hey, since NASA makes this data available, why don't we actually utilize this as well on our website? So we incorporated this Deep Space Network information. So we have a DSN status page as well on our website where you can see what all of the missions are currently communicating with. And then we also, on this slide here that's showing our Horizons information that allowed for our positioning of the Lucy mission, which is headed out to the Trojan asteroids that share an orbit with Jupiter. We also displayed down in the tiny bottom left corner there what dish was communicating with that mission at that time. Now, we're so excited about the Deep Space Network that we also decided, why don't we incorporate it into another one of the websites that we run together. So we run a website called Project Amaze as well, which is our textual and scientific analysis of Andy Weir's Project Hail Mary, which they've just made into a movie featuring Ryan Gosling. And it turns out there's actually a passage in that novel that mentions runs the Deep Space Network. So in one of our posts on there, we decided, hey, why don't we actually integrate that information into the page for our Project Amaze website as well. But those are just examples of how the two of us have decided to use this information. The point is that this information is available to anyone, and you can do all sorts of things with it because it is unrestricted and available to the public. So to further that point, this is a visualization that a colleague of mine at Science World named Dave Malcolm made using a program called Touch Designer, where he made a 3D model of the Earth. And as you kind of spin around here, you can see, the data being kind of uplinked and downlinked from various missions. And that, again, is using that same underlying data that NASA makes available. If you do ever sneak into JPL itself, you can see something called the Pulse, which is this beautiful light sculpture made by an artist named Dan Goods. And if you watch in this video here, those beams of light going up and down represent the actual live data of what those Deep Space Network antennas were beaming up and beaming down at any given time. If the lights are really bright and there's a lot of them, it means there's a lot of data going up or down. So lots of different directions that you can go with that sort of information. Also, we've been saying Deep Space Network over and over again, or at least I have Deep Space Network, right? And so you might be thinking, well, okay, Deep Space Network sounds great. Is there ever such a thing as a shallow space network? On the flip side of things, there is something called the Near Space Network, which is worth mentioning because it communicates with things that are a little bit closer to home, like Earth observing satellites. But the Near Space Network and the Deep Space Network will actually, they have some overlap, right? So both of these will be used in something like the Artemis 2 mission, which is now targeting April to send humans around the moon for the first time in over 50 years. So there's a little bit of overlap there. And also, speaking of things that are a little bit closer to home, or in fact on the ground, something that might be of interest to some folks here is that there are people who use some of this information and set up what's referred to as an amateur DSN. And you can see all of these beautiful dishes that are in many cases in people's front or backyards, where they actually access and know where to point these antennas to those spacecraft as well. And of course, the way that they know where to point those to is by using horizons. So jumping from the ground up into space, right? Because A, no astronomy talk would be complete without pretty pictures taken by space telescopes. But B, it is often helpful to be able to actually send telescopes up and take some beautiful pictures like these, right? Not everything is best done from the ground. So we've seen some beautiful pictures here, and I've just skimmed by them all. A little bit of cosmic eye candy for everyone because, we must. But James, what do you think all of these images have in common?
So perhaps the surprising thing that all these images have in common is that they were taken by, or processed rather, by amateurs. In fact, by one particular amateur in the case of the photos that we just saw, Judy Schmidt. And there are lots of amateurs that do this sort of processing of images from these telescopes, which may raise the question for you, well, hang on a sec. If NASA has got these space telescopes out there, aren't they the ones taking the photos? What on earth's going on with these amateurs? What processing are they doing? Isn't the photo being taken out there? Well, there's a lot of interesting stuff we're going to get into regarding that. But before we do that, I just want to make a quick disclaimer. I know many of you are seasoned astrophotographers. Jennie and I are not experts in astrophotography, so we're not going to claim to say anything about particularly Earth done astrophotography. We're going to focus on the processing of images that come from the space telescope, although there is some overlap, particularly in the tools that get used towards the end of the process in astrophotography. But if you take an image like this, coming back to that question of what is it that is actually being taken by these space telescopes, it's not, in fact, an image like this at all. If you were out there, this is not what you would see. Or to put it another way, if you were on the bridge of the Enterprise looking out the window, it would not look like that at all. Rather, the images that are coming down from the space telescopes look more something like this, these black and white photographs. We'll get into what the variation is between those two photographs in a moment. But I want to illustrate this through a more Earth-grounded example. If you take something like this photograph of a black and white photograph of a rose, you can't really tell much about the color here, right? The whole point of a black and white image is you've lost the color information. But instead of just taking a single black and white photo, I instead took two photos, one through a red filter, one through a green filter, that actually starts to tell you an incredible amount of information about the color of the rose. So by looking at the red filter, you can see how light the petals are. You look at the green filter and see how light the leaves are. And as you might guess, that's because it's a red rose with green leaves. So the point is that by taking black and white photos through different filters, we can actually reconstruct a lot of information about an image. So quick test here. This is 4 photos of a gentleman taken through various filters: yellow, orange, red, and green. Does anyone want to guess what color his toque is? I've been informed it's called a toque. I was going to call it a beanie, but I've been told that's not what you folk call it. Anyone? What color? Red. Exactly right. Okay. Now, in astronomy, we don't really care that much about whether something is red or green. What we tend to care more about is what it's made of. And thanks to the emission lines that the various elements give off, if we know the frequencies of the photons that are coming in, we get a huge amount of information about what the nebula or the star or whatever is actually made up of. Now, the issue there, though, is that the frequencies that we care about aren't broad categories like red or green or blue. They tend to be very fine frequency ranges. And in some cases, we want to distinguish things that are awfully close to one another. So you can see here the hydrogen alpha line and the sulfur 2 line are both very close shades of red to one another. So it's not enough just to use a red filter to work out what's going on there. But what we do is we take photos of the same object using different filters. We've got the sulfur 2 filter on the left, the middle one's the hydrogen alpha filter, and we've got an oxygen 3 filter on the right. And all we care about is the photons that are coming in, so a black and white photo is sufficient. That's what's coming down from, or we'll see in a moment that it's not quite what's coming down from the James Webb Space Telescope or whatever. But you get these different images taken through different filters. But we don't want to just look at this. We want to somehow combine them together, right? We want to be able to see in one image what's going on, what's the sulfur parts, what are the hydrogen parts, what are the oxygen parts, and so on. Now, if we just colored these, I don't know why it jumped. Let me just check what's, no. If we just apply the color that the frequencies correspond to, we'd get something like this. And you can see that there's very subtle difference in the shades of red between the first two, but not much. If we combined all these together into a single image, this is really not, there we go. We'd get something like this, which looks kind of pretty. Certainly doesn't look particularly realistic, but we're not going for realism. Remember, we're going for information. And I don't know if you can see it any better with your glasses there, Jenny.
I was hoping it would help.
It doesn't, does it? Because the problem is that the sulfur 2 line and the hydrogen alpha line are just too close to one another. So what we instead do is not use the actual colors that the frequencies correspond to, and instead map them to slightly different frequencies. And we get something that's often referred to as false color. And that's why this is not what you would actually see if you were out there. What's going on here is that the sulfur 2 line has been mapped to red, pretty close to what it would naturally be, but the hydrogen alpha line in this case has been mapped to green, and the oxygen 3 line has been mapped to blue. So this maximally distinguishes the 3 elements that we care about distinguishing. It makes it very easy to look at the picture and see what are the areas of high sulfur, high oxygen, high hydrogen, and so on. And this particular technique of taking these 3 elements, the frequencies of these 3 element emissions, and mapping them to red, green, and blue respectively, was so common amongst Hubble images that this is often referred to as the Hubble palette. And it's a very distinctive kind of color scheme. Whenever you see images like this, this is the Hubble palette, and it's designed to maximally distinguish sulfur 2, hydrogen alpha, and oxygen 3. Now, this whole idea of using color to convey information has all sorts of applications. One of the simplest ones is in things like old school 3D glasses that Jenny's been wearing this time, right? The point of these glasses is not that you want some things to be in blue and some things to be in red. Instead, you're wanting to use blue to indicate things that are for the left eye, red for things that are in the right eye. But you get other uses as well. There's a Landsat image in the top left showing vegetation in red. You get, detecting heat of a locomotive in this case. In the bottom left, you get a height map where color is being used to convey height. And we talked about this at dinner a bit, medical imaging, in this case a knee that has been coloured to show information. So the point being that we use colour to convey information in all sorts of interesting ways, and that's what's going on with these false colour images that we see like this. Now, there's another reason that false colour turns out to be quite helpful, which is that sometimes the information that we care about isn't conveyed in frequencies that we can see with the human eye. So it's not just about splitting two shades of red that look quite similar to be more distinct. In many cases, we care about things that are happening elsewhere in the electromagnetic spectrum, particularly in the infrared spectrum, which is one reason why things like the James Webb Space Telescope focus so much on the near infrared and the mid infrared, because there's a lot of interesting information for astronomers that is being emitted in those frequencies. And so a lot of the sensors, a lot of the instruments on the James Webb Space Telescope are focused on that particular range of the electromagnetic spectrum, the near infrared and the mid infrared. Now, I talked a couple of times before about the need for identifying a very narrow type of frequency. It's not just a red filter. You want a filter that's going to separate out the sulfur 2 from the hydrogen alpha. And there's a whole full set of filters that exist in the James Webb Space Telescope, and this is in particular the NIRCam instrument, which is the near infrared. You can always identify what the filter means because they're all numbered. They're coded with an F, and then the frequency that they correspond to, and then a letter at the end, W if it's wide, M if it's sort of in the middle, and N if it's a narrowband filter. So that just tells you, what frequencies are being let in. This applies not just to what's going on in the James Webb Space Telescope. You can buy filters like this for your ground-based telescopes as well. These look opaque when you look at them because they're narrowband filters. They're only letting in a very small sliver of a frequency into them. So this is the near infrared. There's another instrument on the James Webb Space Telescope that's doing mid-infrared, and it has another whole set of filters. Now, for these Earth-based filters, rather than having to swap these out on your telescope, you often use something like one of these dials where you put your filters in here and then you can just rotate a dial to switch between which filter you want to take your photo of. The James Webb Space Telescope has a slightly more advanced dial for its filters. This is the filter wheel that is in front of the MIRI sensor, the mid-infrared filter. And you can see all the various frequencies, both wide and narrow and so on, that this is pulling out. When you go look at these photographs, whether they've been processed by amateurs or by NASA professionals, they will often document exactly what they've done. So I encourage you, if you've not done this before, to when you find one of these photos, to go look up, because they'll give this information. So remember, when you get something like F336W, what that means is that it's a filter that's centered on 336 nanometers, but it's a wide pass filter, so it's letting in quite a lot. You get like F657N, which is a narrow filter just letting through the hydrogen alpha. But then what they'll do is they'll say, what color have each of these filter images been mapped to? So the 336W has been mapped to purple, the hydrogen alpha line's been mapped to orange, and so on.
Yeah, and I think just also on that note, right? I think that when you break this stuff down and you are able to see, what's the sort of illusion, it gets dispelled, and what's happening with all of these colors, I think it would be easy at first for someone hearing this information for the first time to almost be disappointed, right? Like oh no, it really doesn't look like that in space. Like that's really disappointing. But I think it actually makes it more beautiful to know that there's all of this science going on behind the scenes in order to make this happen, right? So if you want to end up doing some of this science yourself, one of the places that we recommend to look, and by the way, we'll put a lot of URLs on the screen. You don't have to panic if we fly by them quickly. We collected them all on the last slide. So if you want to take a picture or a screenshot of that, that'll hopefully make your life easier if you're interested in getting into this. But MAST is a fantastic place. And MAST stands for the Mikulski Archive for Space Telescopes. And it's got all of this data from big space telescopes such as the James Webb Space Telescope, Hubble. It will also have the upcoming Nancy Grace Roman Space Telescope data there as well, freely available. And so what you do when you go to MAST is you can search and filter by various different criteria. In this case, very, very small text, I know, but we searched for NGC 3324, which is that cosmic cliffs image that we said was not what you would see looking out the window of the Enterprise. When we did a search for that, we got quite a few results. You can filter it down further by things like the date and time the image was taken, what instrument took it, as well as, importantly, you can filter by what filter was used, because you probably want to use more than one when you're doing this sort of work. So if we select one of these images using one particular filter of the cosmic cliffs here, of course, this will appear in a file format that many of you may be familiar with, and it does not play nicely with a lot of standard software on computers, and that's our friend, the FITS file format, the Flexible Image Transport System. And we've got a few different programs on the screen here that are recommended to potentially use if you want to start processing these images yourself. Fun fact, I happen to know that the computer that is sharing its screen up here right now has at least one of these programs installed on it, because I was sneakily looking at icons on the desktop of things that were familiar to me. So I know some of you may be familiar with these. But let's say I extract this image from this FITS file, and then it ends up looking something like this. And I'm not quite sure what to do with my life at that point. So James, what do I do with my life?
Right. You may have deliberately downloaded a file you thought was of a particular nebula that you were going to make a wonderful image of, and you see this and you're like, I don't really see the nebula. What's going on here? Well, the problem is that image like this that is, I can't remember whether this was Hubble or JWST. It doesn't really matter for the point. Is that this is a 12-bit image, and so there are 4,096 different levels of brightness. The problem is most of the photons that are coming in are at a brightness that's way down in the dark end. And the problem with that is that by default, the way that we display these images is the lowest brightness is what it takes to make black, and the highest brightness is what it takes to make white, which means almost nothing is much above black. And so the first step we can do is basically pull up how dark something has to be considered black, the so-called black point, and we can push down how bright something has to be considered white, the so-called white point. If we do that for that image we just saw, we get something more like, oh, I think I've gone too far. We get something like this. And now you can see it's the Horsehead Nebula, although it's a little too blown out. The problem is that we don't actually want a linear relationship between these things. And so there's another technique we can do, which is to actually use a curve. And this is almost universally done with images. I'm sure many of you who've done astrophotography have done this at some point. It's often referred to as stretching, where you're basically deciding what's going to be black, what's going to be white, and what the curve between them is going to be to really maximally bring out the features and the contrast. So this is something you typically do for each of those filter images that you've downloaded before getting to the final step, or maybe the penultimate step of deciding what color you're going to map each of these to. And this can be done in any photo application that lets you have different layers and affect the color. So in this case, it could be Photoshop even, or GIMP and so on, where you're assigning a color to each of those images you've gotten from a filter. And so to sum up, yep, there we go. You take, in this case, 6 different filtered images, you assign them colors and combine them, and then typically as a last step you do a little bit more work on the curves just to bring out the contrast a little more, and you end up with a gorgeous image like you see on the right-hand side. It's aesthetically very pleasing, but it's also got a lot of scientific content in as well, because the colors correspond to something that's meaningful in terms of the underlying element emissions.
So all of those images that we've been talking about thus far were primarily things that had to do with, the Hubble Space Telescope, James Webb Space Telescope, things that you could find on MAST. Have I gone too far? What will occur now? It's a mystery. But I did want to share one other source of astronomical images where all of the raw image data is available that I highly recommend looking into. We mentioned the Juno mission a couple of times, the Juno mission to Jupiter. So that one of the instruments, JunoCam, actually does make all of its information and data available as well. What's really wonderful about the JunoCam website is that this whole lovely community grew up around it, where people were voting on different targets for the instrument. They were, giving feedback on each other's photos and things like that. And of course, similarly, you can search by different points of interest on Jupiter or its moons, and various different filters and things like that. One of the things I really love about this, though, is that the JunoCam community got quite creative with their output. So you get things like this, where people went in quite a aesthetic and artistic direction with their art. In fact, if for some reason you have just always thought that Jupiter might be better off if it were a cube, you can actually make that sort of thing happen by using the raw image data. And this, that's one of the images that I found on the JunoCam gallery there. So the possibilities really are limitless when you have access to this data. Whatever you are dreaming of creating, you can absolutely create that thing. But of course, we're coming up pretty shortly here to the end of our showcase of some of our favorite sources of data. What that means is that I do want to give you a very quick whirlwind tour through some, not all, but some of the other data sources that are available. Because again, there's an incredible amount of data that NASA makes available to anybody. And chances are, whatever cool thing in space you are interested in, whatever mission, whatever type of object you are interested in, wavelength of light even you are interested in, there's probably a data source that is publicly available for you to access. So one of the examples here, the planetary data system, and specifically the small bodies node. I really like asteroid. I've given a lot of presentations about asteroids. So I'm a big fan of the Lucy mission going to those Trojan asteroids around Jupiter. The Lucy mission did kind of a tech check by doing a flyby of a main belt asteroid called Donald Johanson. You can get all of the raw data from one of the imagers on the Lucy spacecraft. All of that is available, right? The sort of things that I would have thought would only be available to the Lucy team at NASA. You can also get all of the data from the OSIRIS-REx mission, in which we flew a spacecraft out to the asteroid Bennu, which turns out to be a great big rubble pile in space, grabbed a bunch of pieces of it, flew them back to Earth, and are actually analyzing those samples. You can look at all of that information as well. Now, if you're feeling a little bit more high energy about this sort of thing, if you like those high energy wavelengths of light, you can actually access this astronomy archive from NASA that gives you things like data from all extreme ultraviolet, X-ray, and gamma ray information. Under this website as well, they house some stuff about the cosmic microwave background and research that's been done with various space telescopes and instruments on that as well. Again, all freely available, unrestricted for anyone to use. This astromat.org is a great place to look at sample-related data. And again, anything that would be available to the scientists is just free and open to use for whatever sort of creative projects you would like to do with that. That includes everything from lunar sample information from the Apollo missions to information about various meteorites that have landed on Earth, and even in some cases, cosmic dust or comet dust in the case of the Stardust mission that flew through the trail of a comet. All of that data is available as well. And of course, bringing it back closer to home, NASA does have this suite of Earth observing satellites and Earth observing missions that tell us a lot of important things about our planet and how our planet is changing. And again, all of that information is freely available, not just to the experts at NASA, but also to amateurs.
And I just want to take this opportunity as to put my linguistics hat back on and say something about the word amateur, because often we take it to mean somebody that's not an expert, that isn't a professional. But I just want to point out the original meaning of the word amateur. And you can sort of guess it if you know Latin or French or Italian or Romance language. It's somebody that does something just for the love of it. And I'm sure you can all relate to that. That's the real meaning of being an amateur, is doing it for the love of it. And thanks to the information that NASA has made available, we can pursue our loves in really amazing ways. So we've talked a little bit about what we've done with NASA data and exploring our horizons, but I hope you're all encouraged to take some of that same data and use it to explore your horizons as well. So thank you very much.
Thanks so much.